We live in a world that is just absolutely flooded with data. And trying to find the information that actually matters, it can feel like searching for a needle in a cosmic haystack. Today, we're going to dive into how machines are being taught to find that needle. I mean, think about it. For pretty much any problem you can imagine, whether it's diagnosing a disease or predicting the stock market, we can collect just a staggering amount of information. We're not just collecting a few data points, we're collecting everything. We're practically drowning in it. And that leads to the million-dollar question, right? With all of this data flying around, and more importantly, how do our machines figure out what the real meaningful signal is and what's just distracting noise? Okay, to really wrap our heads around this, let's start with a really simple real-world example. Let's say we were trying to distinguish between these two communities. Our brains, almost instantly, would probably pick up on a key physical difference. On average, one group tends to be taller than the other. In this case, height is a really powerful feature that helps us tell them apart. But here's the catch. A human can make that intuitive jump. A machine, on the other hand, gets a spreadsheet with maybe 40 or 50 different measurements for each person. Things like weight, shoe size, arm length, you name it. It needs a systematic way to automatically figure out that height is the one that really matters. It needs a formal process to follow. And that whole formal process, it actually has a name, and it's absolutely fundamental to how modern AI and machine learning works. It's called feature selection, and really, it's just the art and science of automatically picking the most important, most relevant variables or features from all your data, so you can build a better predictive model. So the whole point here isn't to just use everything you've collected. The goal is to take this huge, messy pile of initial features, we can call the total number n, and intelligently shrink it down to a much smaller, way more potent subset, which we'll call B. So you're probably thinking, okay, but why? Why go through all that trouble? Why not just throw all the data at the computer and let it sort it out? Well, it turns out that in the world of machine learning, less is very often more. There are three huge benefits. First, it just makes things simpler. Fewer features mean your models train faster and are way easier to understand. Second, you're actively getting rid of noise. A lot of data is either totally irrelevant or just repetitive, and ditching it helps the model focus on what counts. And finally, it gives us amazing insights. By seeing which features the machine picks, we start to understand what's really driving the results. Let me give you a super simple example of what we mean by noise. Let's say we're collecting data, and we have one feature for a person's weight in kilograms, we'll call it X1, and then we have another feature for their weight in pounds, X2. I mean, think about it. One is just a direct calculation of the other. They are providing the exact same piece of information, just in a different unit. So keeping both doesn't add any new knowledge at all, it just adds clutter. Do we really need both? Of course not. It's redundant. Okay, so the plan is to just pick the best, smallest set of features. Sounds pretty straightforward, right? Well, this is where things get really, really interesting. Your first instinct might be to say, hey, why don't we just test every single possible combination of features? If we want the best 10, let's just try all the groups of 10 and pick the winner. This is what's called an exhaustive search. But let's look at the brutal reality of that idea. If you start with just 100 features, which is pretty small for a modern problem, and you want to find the best possible subset of 10, the number of combinations you'd have to check is over 17 trillion. Trillion. It is just fundamentally impossible to check them all. And here's the real kicker. Even if you could check them all, you would run into this wild, mind-bending paradox summed up perfectly by this famous quote. The two best features are not necessarily the best two. What on earth does that mean? Let's break it down. Imagine you test your features one by one. Feature A is an absolute rock star, 90% accurate all by itself. Feature B is also fantastic at 88%. And then there's feature C, which is just okay at 60%. So logically, the best pair of features has to be A and B, right? But then you actually combine them, and look what happens. A plus B gives you 91% accuracy, a tiny improvement. But when you combine the best feature, A, with that supposedly weaker feature C, bam, 95% accuracy. How is that possible? Well, it's likely that A and B are redundant. They're telling you similar things, like our weight in kilos and pounds example. But C, even though it's weaker on its own, is bringing some totally fresh, complementary information to the table. And that paradox is what makes feature selection so tricky. So, if we can't just brute force it by checking every combination, and we can't just pick the top individual players, what in the world are we supposed to do?
Well, the modern approach basically boils down to a two-step game plan. First, you define what's called an objective function. You can just think of it as a scoring rule. We'll call it J, that can look at any group of features and give it a grade for how good it is. Then, second, you unleash a clever search algorithm to explore that massive space of 17 trillion possibilities to find the combination with the highest J score, all without having to check every single one.
And this isn't just theory. This flowchart you're looking at, that's a real-world blueprint for exactly how this is done. You feed the raw, messy data into the system, it uses these methods to intelligently select the most critical features, and then it passes that clean, powerful signal onto a classifier to make a final, accurate decision. So we've covered a lot, but I want to leave you with one final thought. And it's that this problem is, well, it's far from being completely solved. Truly understanding the deep, complex, sometimes hidden relationships between different variables is still a massive frontier for research. How much one feature depends on another and how they all interact in weird and wonderful ways, that's a question that statisticians and AI researchers are still working on every single day. And this leaves us with a really big, important question, doesn't it? As we hand over more and more of our world's complex decisions to AI systems, the features they choose to focus on become the very basis of their logic. So the ultimate challenge isn't just about building an accurate system. It's about making sure it's focusing on what's truly important and what's fair. And that question is something we'll be grappling with for years to come.